Welcome to today's paper reading. Today's paper is titled EAGLE-2, Faster Inference of Language Models with Dynamic Draft Trees. This paper was published on the AR14 preprint by Yuhui and colleagues from Peking University, Microsoft Research, University of Waterloo, and Vector Institute. The abstract highlights the challenges of inference with large language models, LLMs, which are both expensive and time-consuming. Speculative sampling, particularly through methods like EAGLE, has been identified as an effective solution. However, the authors discovered that the acceptance rate of draft tokens is not only position-dependent but also context-dependent. Building on EAGLE, they propose EAGLE-2, which introduces a context-aware dynamic draft tree. This innovation leverages the well-calibrated draft model of EAGLE, achieving significant speedups of 3.05x to 4.26x, which is 20% to 40% faster than EAGLE-1. The evaluations were conducted across 3 series of LLMs and 6 tasks, demonstrating that EAGLE-2 maintains the distribution of generated text, ensuring a lossless acceleration algorithm. Modern large language models, LLMs, exhibit impressive capabilities and are widely applied across various domains. However, their parameter sizes have grown substantially, even exceeding hundreds of billions. During autoregressive generation, each token generation requires accessing all model parameters. In a single dialogue, hundreds to thousands of tokens might be generated, making LLM inference slow and expensive. Speculative sampling methods aim to address this issue by rapidly generating draft tokens and then verifying them in parallel. These methods generate multiple tokens in a single forward pass, significantly reducing inference latency. Figure 1 illustrates the speedup ratios of various inference methods at a temperature of 1. Notably, the Vicuna series employs Vicuna 68M as its draft model, while Llama 2 Chat does not have a suitable draft model, hence marked as not applicable. Additionally, methods like Medusa modify acceptance conditions under non-greedy settings, which compromises the guarantee of lossless acceleration. This study exclusively contrasts speculative sampling methods that maintain the output text distribution. Figure 2 illustrates the speedup ratios of various inference methods at a temperature of 0. For speculative sampling, the Vicuna series employs Vicuna 68M as the draft model. Models like Llama 2 Chat 7b, 13b, and Llama 3 Instruct 8b, which lack suitable draft models, are marked as not applicable. Additionally, Llama 2 Chat 70b and Llama 3 Instruct 70b utilize Llama 2 Chat 7b and Llama 3 Instruct 8b as their draft models, respectively. These findings are further detailed in Table 1. In speculative sampling, the process involves drafting a potential sequence using a smaller model and then verifying it with the original larger model. EAGLE enhances this by performing autoregression at the feature level before the language model head, and it uses a tree-structured draft for verification. EAGLE-2 further refines this by dynamically adjusting the shape of the draft tree based on the context, allowing for more efficient and accurate predictions. Figure 3 compares the standard speculative sampling method with EAGLE. It highlights that while EAGLE employs a tree-structured draft during the verification stage, the standard method uses a chain-structured draft. The figure also notes that TI represents the ITH token embedding and Phi represents the ITH feature vector in the second-to-top layer of the LLM before the LM head. Figure 4 illustrates the differences between EAGLE and EAGLE-2 in their approach to draft tree shaping. EAGLE maintains a fixed draft tree structure, which can lead to unnecessary candidate additions, such as predicting 3 after 10 plus 2 equals. In contrast, EAGLE-2 dynamically adjusts the draft tree based on the context, adding only one candidate 1 for the same query. This context-dependent adjustment aims to improve the efficiency and accuracy of token prediction. In this section, we examine the acceptance rates of draft tokens in dynamic draft trees. We found that these rates are significantly influenced by the position of the tokens within the tree. Specifically, tokens at position P1 have the highest acceptance rate, while those at position P6 have the lowest. Tokens in the upper left part of the tree generally have higher acceptance rates compared to those in the lower right. However, we also observe that the acceptance rate at the same position can vary widely, indicating that context plays a crucial role in determining whether a token is accepted. This suggests that a context-aware dynamic draft tree could be more effective than a static one. Additionally, we explored the relationship between the draft model's confidence score and the acceptance rate of tokens. We discovered a strong positive correlation. Tokens with a confidence score below 0.05 have an acceptance rate of about 0.04, while those with a score above 0.95 have an acceptance rate of approximately 0.98. This finding allows us to estimate acceptance rates using the draft model's confidence score, facilitating dynamic adjustments to the draft tree structure. Figure 5 illustrates the acceptance rates of draft tokens at various positions within a token tree. The left figure labels positions P1 through P6, which correspond to positions 1 through 6 on the horizontal axis of the right figure. The right figure displays the acceptance rates of draft tokens at these positions. Notably, the highest acceptance rate is observed at position P1, while the lowest is at position P6. Additionally, there is significant variance in acceptance rates at the same position, indicating that context plays a role in token acceptance. EAGLE-2 is an acceleration algorithm designed to enhance the inference process of large language models by dynamically adjusting the draft tree. This algorithm specifically targets two key aspects: the expansion of the draft tree and the re-ranking of draft tokens. During the expansion phase, the algorithm selects the top K tokens with the highest global acceptance probabilities from the current layer of the draft tree and uses tree attention to compute the probabilities for the next tokens in a single forward pass. This process helps in expanding the draft tree efficiently. In the re-ranking phase, all draft tokens are re-ranked, and the top N tokens with the highest values are selected. This ensures that the tokens used in the verification phase are optimal. Additionally, the attention mask is adjusted to maintain consistency with autoregressive decoding, ensuring that each token can only see its ancestor nodes. Figure 6 illustrates the strong positive correlation between the draft model's confidence score and the acceptance rate of tokens. Tokens with a confidence score below 0.05 have an acceptance rate of approximately 0.04, while those with a confidence score above 0.95 have an acceptance rate of about 0.98. This correlation allows for the estimation of acceptance rates without additional overhead, facilitating dynamic adjustments to the draft tree. In this section, we discuss the models evaluated, the tasks assessed, and the evaluation metrics used. The models evaluated include Vicuna 7b, 13b, Llama 2 Chat 7b, 13b, 70b, and Llama 3 Instruct 8b, 70b. The tasks assessed are multi-turn conversation, code generation, mathematical reasoning, instruction following, summarization, and question answering. The evaluation metrics used are speed-up ratio, average acceptance length Chao, and hardware-independent metrics. These metrics are crucial for assessing the acceleration performance of the models without compromising the generation quality. Figure 7 illustrates the EAGLE-2 process with dynamic draft trees. The numbers beside the edges indicate the confidence scores from the draft model, while the numbers within the blocks represent the node values. In the expansion phase, the top two nodes with the highest values from the current layer, highlighted in orange, are selected as inputs to the draft model, and the generated tokens, in green, are connected to the draft tree. During the re-rank phase, the top 8 nodes with the highest values from all nodes, highlighted in blue, are selected, flattened into a one-dimensional sequence to form the final draft. An attention mask is then constructed according to the tree structure, ensuring each token can only see its ancestor nodes. Table 1 presents the speed-up ratios and average acceptance lengths, Chao, for various methods across different models, specifically Vicuna, V, and Llama 2 Chat, L2. Standard speculative sampling, SBS, is noted with its draft model as Vicuna 68M. Methods that relax acceptance conditions under non-greedy settings, such as Medusa, are not included in the comparison as they do not guarantee lossless acceleration. The table highlights the performance metrics for each method, providing a comprehensive view of their efficiency and effectiveness in different scenarios. In the field of large language model, LLM, inference acceleration, several methods have been proposed. These include low-bit quantization, pruning, and knowledge distillation. These techniques aim to reduce computational costs but often at the expense of model performance. Speculative sampling methods offer a different approach, achieving lossless acceleration by using the original LLM for verification. Early methods focused on greedy settings, but recent advancements have extended this framework to non-greedy generation. Dynamic draft trees, such as EAGLE-2, represent a significant advancement by allowing flexible adjustments to the draft tree structure, resulting in improved performance without structural limitations. Table 2 presents the speedup ratios and average acceptance lengths, Chao, for 3 different LLM models, Llama 2 Chat 70B, Llama 3 Instruct 70B, and Llama 3 Instruct 8B. The data is collected with the temperature set to 0 on the empty bench dataset. The table compares the performance of EAGLE-2 with other methods like PLD and Look-Ahead. Key metrics include the significant speedup achieved by EAGLE-2, particularly with the Llama 2 Chat 70B model, where it achieves a 3.51x speedup and an average acceptance length of 4.48. This demonstrates the efficiency and effectiveness of EAGLE-2 in accelerating LLM inference without compromising on quality. Table 3 presents the results of an ablation study conducted with the temperature set to 0 on the Vicuna 7B model. The study examines the effects of not using value, confidence score, and not performing re-ranking on the speedup ratio and average acceptance length. The results show that both value and re-ranking significantly improve performance on the empty bench and GSM-8K datasets. This highlights the importance of these components in optimizing the model's inference speed and token acceptance rate. In this paper, the authors introduce EAGLE-2, an efficient and lossless speculative sampling method. They found that EAGLE's draft model confidence is a good approximation of the acceptance rate for draft tokens. Based on this, EAGLE-2 employs a context-dependent draft tree structure, which significantly increases the number of accepted draft tokens and results in better speedup ratios. EAGLE-2 ensures that the generated results are consistent with the original large language models, LLMs, and does not require additional training. The authors conducted extensive evaluations using various LLMs across multiple datasets and compared EAGLE-2 with several state-of-the-art speculative sampling methods. In all their experiments, EAGLE-2 achieved the highest speedup ratios. Thank you for watching.